Welcome to this lecture on direct current generators. We move on. We'll be covering generating an AC voltage. We start from there and then move on to direct current generator. Have the AC generated AC voltage can be converted, and then how you could improve the wave shape. What's the induced voltage and its value? Some mathematics there. And then winding configurations and what is armature reaction. Then we go into different types of generators, namely separately excited DC generator, shunt, and the compound generator. So those are the things that we want to cover. Let's move on. Now if you got a set of permanent magnets, a north pole and a south pole, winding in the middle, of which the two terminals are taken out from A and D, and then they are connected to two slip rings like this. These are called slip rings, and then there are two brushes electrically in contact with the two slip rings. From these two brushes X and Y, there is a conductor supplying whatever it is generated in the winding to a load. Now if by some means, if we start rotating this winding inside this magnetic field, then we know that from what we have discussed so far in magnetics, we know that if the closed conducting loop is rotating inside a magnetic field, there will be a voltage induced between the terminals of that winding. So because of that basic principle, we will be generating a sinusoidal voltage like shown in this graph at the outputs of the brushes, which is acting on the load. So as we know, this is an AC voltage. So this is a very basic AC generator. This system can generate a sinusoidal signal. But how could we make it DC or direct current? This is what we do. Instead of the continuous slip rings, we get the two terminals of the two windings, and instead of the two continuous slip rings, we make half of the slip ring two halves of slip rings. One half is connected to one terminal, the other half is connected to the other terminal. So and the brushes are connected like this, where this is the plane. If you consider this vertical plane, that's important. The two brushes are now in a vertical plane, and when this winding is aligned with that vertical plane, as you can imagine, which is when this winding is vertical, there is no voltage induced in the winding, because for a slight movement from that vertical position, the conductors are not intercepting any of the flux lines. Because of that, there is no induced EMF. So this arrangement, when the winding starts rotating, will produce this type of a voltage. So as you could see, as I said, when the winding is at 90 degrees or 270 degrees, it is generating 0 voltage. So in this arrangement, the key thing is to place the brushes in this 0 position, which is the vertical plane in this case. Now suddenly we've got a DC generator or a direct current generator, because as you could see now, there is no negative half cycle. The induced EMF is only positive. Of course it touches 0, but it doesn't become negative. Then now the challenge is This is not constant, you see, so it fluctuates. So how could we get a better voltage signal or improving the wave shape? This is what we do. Instead of having just 2 poles, you could make it 4. So now two windings perpendicular to each other, and 2 sets of brushes or 4 brushes. Each winding is connected to 2 of these brushes. Still, the brushes that takes this voltage signal out is still in this vertical plane, which is the magnetically 0 position. By increasing the number of coils and segments, we can obtain a DC voltage that is very smooth. Modern DC generators produce voltages having a ripple of less than 5%. So now this one, as you could see, produces this kind of voltage. So there is no coming down to 0, but still there is ripple. Now what we say here is that there are modern machines which reduces the ripple down to less than 5%. So ripple, the way you calculate the percentage ripple is you get the maximum change. This is your average, so you mention it as the percentage of the average. So it could be as less as 5% in modern machines. Let's move on. Now we look at a couple of equations. What is the induced voltage and its value? The voltage induced in DC generator having a lap winding is given by the equation E naught is the induced EMF is equal to Z times N times phi divided by 60, where E naught is the voltage between the brushes, Z is the total number of conductors on the armature, N is the speed of rotation, and phi is the flux per pole. So that's the induced voltage. N, please remember, is the speed of rotation in RPM. Now we look at the armature conductors. Now the windings in a DC machine are arranged in coils in order to multiply the number of conductors in action. So not just one conductor, but a bunch of conductors. Then you intercept a large number of conductors, intercept the flux, so you get more voltage. So in a DC generator, this increases the induced voltage, whereas in a motor, this increases the torque produced or applied on the conductors. And this leads for us to talk about winding configurations. There are different ways of winding the armature. So there are 2 basic types of windings: lap winding and wave winding. There are diagrams in Wheel D. The coils ends terminated in adjacent commutator segments. This is called the lap winding arrangement. Coil ends terminate in adjacent commutator segments. I've got some figures coming up soon. The configuration determines the number of parallel and series conductor paths, hence the output voltage and the current capability. Now these are the windings. So lap winding goes like this, right? The wave winding, in between the brushes, it goes like that. So this is a 4-pole lap winding, the figure of a 4-pole lap winding, and these are the brushes. So please have a look at the figures on your own later. You won't be able to follow everything as you just look at them, but just these figures are from the text, or you can replay the video and see. So more about lap winding. Conductor starts from a commutator segment, traverses two pole faces, and is terminated in an adjacent commutator segment. The voltage generated from these pole faces are additive, so they add together. Coils are interconnected at the commutator in a series configuration between each set of brushes. So that's lap winding. What is wave winding? This is wave winding. It's complicated, you can have a look at it later. So the description is: conductor starts from a commutator segment, traverses two pole faces, and is terminated in a commutator segment near diagonally opposite. So that's the difference in the wave winding. Pattern is repeated. The coils are connected in series between each set of brushes. Conductors in a wave winding are under the influence of all pole faces as against localized influence for the lap winding. So that makes the difference between the wave winding and the lap winding. Next important thing is the brush. Brushes are there to collect the current flowing out from the commutator. Brushes are placed in neutral position. I showed you what the neutral position is in that very basic arrangement. Neutral position to ensure spark-free operation. The number of brush sets equal the number of poles. Neutral positions are those places on the surface of the armature where the flux density is 0. I showed you that. When the generator operates at no load, the neutral zones are located exactly between the poles, as I showed. No voltage is induced in a coil that cuts through the neutral zone. Generator operates at no load. The neutral zones are located exactly between the poles. When the generator is operating at no load, they are exactly between the poles. But we got some comments on the brush position. Locating the brush at neutral zone is the important thing for better or the acceptable commutation, because when there is no voltage induced at these positions, as the commutator moves from one segment to the other, there is no short circuit taking place. Load current flowing in an armature circuit creates, but what happens is, when a load current is flowing in the armature circuit, it creates its own magnetic field, because armature will start flowing currents. There will be armature currents flowing in. So it creates another magnetic field, addition. So this is called the armature reaction, and it can cause arcing in the brushes. Why it happens? Now this is the situation. This is the first figure, shows the flux, magnetic flux traversing in the stator and the armature due to the stator windings. And when it is loaded, when the machine is loaded, when current starts flowing in the armature, these are the magnetic flux lines created by the armature currents. So the resultant flux paths in the magnetic circuit will be like this. It won't be symmetrical as it was before, but there will be certain deformation, which means the magnetic neutral position will no longer be this horizontal plane which we used before to place the brushes. So that is the armature reaction. So because of the armature reaction, when you place the brushes in the geometrical neutral position, or the exactly in between the poles, which we think as the neutral position magnetically, brushes will start arcing. So one possibility is adjust the position of brushes to align with the neutral position. This is adopted in older DC machines. So if you look at an older DC machine, they've made it possible for the set of brushes to be slightly adjusted. You can loosen the screw, shift the brushes and tighten it again. So you could change it. However, since the degree of armature reaction depends on the load current, an operator will have to be on standby to adjust the brush position should there be changes in the load current. Now, this is a big problem because not all the DC machines operate at the same load. If the load is constant, fine, but it is not. So if the load current changes, magnetic neutral will change, which means you have to readjust the brush position. So any motor operating under varying load, changing the brush position is not the best technique, because an operator cannot do it while the machine is working. Because of that, there are some other methods. One is use of commutating poles. So you introduce commutating poles in between the poles of the machine to create some kind of a additional flux, which will try to bring the brush position to the neutral position. A better method is to use commutating poles positioned in between main poles and connected in series with armature winding. When the commutating poles are connected correctly, it counteracts the armature reaction generated by the main current. So that's the purpose of the commutating poles, or they are also called interpoles. Then we move on to different types of generators. The first one is separately excited generator. Now, what is separately excited generator? Now, what happens there is a DC generator whose air flux is produced from a field winding which is supplied from an independent external DC source is called a separately excited generator. In case of such a generator with a field winding, the greater the speed and field current, the larger is the generated EMF. You could say that's the ideal situation, but in practice there are some other complications. Let's talk about them later. Now, this is a schematic. As you could see here, now this is the winding, the field winding, which is separately supplied from this supply. This is the source supplying the field winding, and this is the output of the generator. The electrical circuit is like this. You got a separate circuit for the field. It's completely independent from the load circuit. So that's the armature supplying the load. So some mathematics here. Armature current IA is the same as IL. IA, the armature current coming out, is the same as IL. The terminal voltage appearing at these terminals. Remember, there is an internal resistance here, so you got to reduce the resistive voltage drop of the internal resistance. So the terminal voltage V can be written as EG, which is the induced EMF inside, minus the armature current times the resistance, armature resistance, IA RA, and the electrical power developed will then be EG times IA, because that's what is developed inside. The power delivered to the load will be that minus the resistive voltage drop. So immediately there comes the efficiency issue, because there is a internal resistive loss here. EG IA minus IA squared into RA. Substituting from here, we can write IA times EG minus IA RA, which is the same as V times IA. That's the power delivered to the load. Now let's look at no load operation and what is the saturation curve. The magnetic saturation we discussed earlier comes into picture. At no load, armature circuit is open, and a change in the exciting current causes a corresponding change in the induced voltage, which is fine. When you increase the exciting current, as exciting current continue to rise, the iron in the field and the armature begins to saturate. So as you increase the field current, the magnetic circuit inside can become saturated. So a large increase in the magnetic MMF is now required to produce a small increase in flux. So that is the effect of saturation. So because of that, you cannot infinitely increase the field. That's why we said ideally the higher the field current, the larger the induced generated voltage, but that's not the case in reality. There is a limit because of the fact that your magnetic circuit gets saturated. Now when it comes to the loading situation, separately excited generator under load, when the load increases, obviously the terminal voltage diminishes progressively because of the fact that the voltage drop of the internal resistance in the armature becomes more and more significant. Because of that, there will be this kind of a drop as the load current increases. So this is the equation which governs this E12, which is again the terminal voltage, is E0 minus I times RA. Simple voltage relationship. Self-excited DC generators, what are they? Now they are the generators where the field flux is supplied by a winding fed from the current from the output of the generator itself. They are called self-excited generators. Unlike separately excited, where you got a separate source, you use the voltage generated from the generator itself to supply the field winding. And then there can be three main types: series generator, shunt generator, and compound generator. What are they? Series generator. Now in the series generator, the field winding is connected in series with the armature winding. So this is the one which produces the field flux. In a series wound generator, the field winding is connected in series with the armature winding, so that the whole armature current flows through the field winding as well as the load. Armature current IA, which is the same as ISE, is equal to IL is equal to I. Sorry, the typo here. Terminal voltage V is equal to EG minus I times RA plus RSE. RSE is the field resistance, winding of the resistance of the field winding. RA is the resistance of the armature winding. Power delivered in armature is equal to EG times IA. EG times IA is the power delivered to the armature. Power delivered to the load, as before, you just subtract, or just subtract the power dissipated in the armature resistance and the field resistance. It's the same as terminal voltage times the current gone into the load. So that's a bit of mathematics. Shunt generator. Now there the field winding is connected in parallel with the load to the armature. In a shunt generator, the field winding is connected in parallel with the armature winding, so that terminal voltage of the generator is applied across it. The shunt field winding has many turns of fine wire having high resistance. Now since the full voltage is applying, generated voltage of the DC generator is applying across the field winding, you have to have larger number of turns with fine wire having high resistance, so that the current going in this way, the field current, is reduced. So the shunt field current is the voltage divided by the field resistance. Armature current is the addition of the load current plus the field current, which is Ia. Terminal voltage V again is the induced EMF minus the armature current times the armature resistance, and the power delivered in the armature again is Eg times Ia. Power delivered to the load is V times IL, but you should remember the fact that there is another current component out of this Ia going towards the field winding. Now in case of a shunt generator, the easy way of controlling the voltage is to have a variable resistor or a rheostat connected in series with the field winding, and changing this will change the field current. Simply vary the exciting current by means of a rheostat connected in series with the shunt field, and depending on the shunt field resistance, you could have different operating points. That's what is shown in the figure. The no load voltage depends upon the resistance of the shunt field circuit. You can use different points in this magnetic saturation curves to get the no load, set the no load voltage. And then the shunt generator under load, what happens is the exciting current falls as the terminal voltage drops, and the terminal voltage falls off more sharply with the increasing load. I've missed some text here, sorry about that. For a self-excited generator, the drop in voltage from no load to full load is about 15% of the full load voltage. That's for a self-excited generator, whereas for a separately excited generator it is usually less than 10%, and this way of expressing the drop is called the voltage regulation. Now we come to compound generator. It was developed to prevent the terminal voltage of a DC generator from decreasing with increasing load, because in both previous occasions, no matter if it was separately excited or self-excited, the terminal voltage drops as the load increases. So to counteract that problem, they came up with this compound generator, where you got two segments of winding. One is in series with the armature, the other one is in parallel, similar to a shunt generator, except that it has a additional field coils connected in series with the armature. This is a schematic, so you could see this is the series field and this is the shunt field. This winding is the series winding and this is the shunt winding. It is connected, yeah, like that in shunt. Electrical circuit looks like this. What's the difference? Compound generator, one classification is called short shunt, in which only shunt field winding is in parallel with the armature winding. So shunt field winding is in parallel with the armature winding. If it is called long shunt, in which the shunt field winding is in parallel with both the series field and the armature winding. Series field and the armature winding are in parallel with the shunt field. That's called long shunt. Short shunt and long shunt. Now, a couple of equations for the short and long shunt versions. Series field current ISE is IL equal to IL. Yeah, the same current, the load current goes through series field. shunt field current ISH is equal to V, the terminal voltage, plus the voltage drop across the series field winding divided by the series field winding shunt field winding resistance. Terminal voltage V is the generated voltage Eg minus Ia times Ra is the resistive voltage drop across the armature winding, minus ISE times RSE is the resistive voltage drop across the series field winding. Power developed in the armature is Eg times Ia, straightforward. Power delivered to the load is V times IL. For the long shunt, there is slight difference. Series field current is the same as the armature current, which is equal to the load current plus the shunt field current. Shunt field current is equal to the terminal voltage divided by shunt field resistance. Terminal voltage is equal to generated voltage Eg minus the voltage drop across the armature winding, resistive drop across the armature winding, plus the resistive drop across the series field winding. And the power developed in the armature is same as before, and the terminal power delivered to the load is same as before. Now there is a slightly different classification depending on how the flux components of the series field and the shunt field are interacting. We call it cumulatively compounded DC generators if the flux produced by the shunt and series windings are such that they add together to produce a higher output voltage than the on-no load. So then the output voltage, as you can see, will be higher as the load current increases. Overcompounded generators. Now in some cases it is required to compensate not only for the armature voltage drop but also for the IR drop in the feeder line when the generator supplies a certain lengthy transmission line which connects the generator to the load. If that is the case, then the drop in the feeder should also be compensated to get the nominal rated voltage at the load end. So then we use this over compounding. What we do is we add couple of additional turns in the series field winding so that the terminal voltage increases as the load current rises. That is over compounded. And the other version is differential compound generators. Now in a differential compound generator, the MMF of the series field acts opposite to the shunt field. So then as the load current increases, the field flux drops. So the terminal voltage falls drastically with increasing load because of that. Now formerly used in DC arc welders because they tended to limit the short circuit current and to stabilize the arc during the welding process. So differential compound generators are for special purposes because that is not to maintain the output voltage constant, but it drops. So this is how the load characteristics of all these different types of generators. Differential compound, you can see a drastic drop. Shunt, separately excited. Compound is better, and over compound, as you can see with the load, actually the terminal voltage increases. So that's the load characteristics. That brings us to the summary. So what we discussed, these things, machines commutate well when the brushes are located at the neutral zone. and the load current causes armature reaction that shifts the neutral zone or the magnetic neutral, resulting in sparking at the brushes. Armature reaction can be counteracted by introducing interpoles or commutating poles. For large heavy-duty DC motors, compensation windings are mounted on the main pole face to further counteract the effect of armature reaction. And then different types of DC generators have been made to produce different load characteristics. So that brings us to the end of the discussion on DC generators. Thank you.